Thank you for joining the Capital District Regional Planning Commission's fifth webinar of our Climate Action webinar series, where we will be learning about how air source heat pumps and geothermal heat pump energy networks are being installed in the capital region. My name is Josh Dranoff. I am a Senior Sustainability Planner on the CDRPC Sustainability Team. I have just a few housekeeping items I'd like to cover. So the webinar will be recorded and posted to our YouTube page and our website. We'll have time throughout the webinar to take questions, so feel free to post them in the Q&A box at the bottom of your screen. So this webinar series supports CDRPC's Climate Action Plan, completed last year with federal funding through an extensive regional and local stakeholder engagement process. The plan available on the CDRPC website includes 67 voluntary measures focused on reducing greenhouse gas emissions in all major sectors: the built environment, transportation, agriculture, waste, and industry and refrigerants. CDRPC's outreach team can work directly with communities to review these measures and identify local action that support climate goals. The webinar series is part of an ongoing outreach effort, providing additional knowledge and resources to help communities see how some of these measures are already being implemented and planned sustainably to reduce emissions. So with that, I'd like to introduce today's webinar speakers. We have Aeowyn Kendall, Staff Hydrologist, GHX Design Specialist, and Chris Winckler, Business Development at Aztech Geothermal, based in Boston Spa, New York. Aeowyn Kendall does commercial ground heat exchanger designs using software tools, including Gaia GLD. She also creates site geological studies to help with understanding the unconsolidated and bedrock layers, along with hydrology, which impact the thermal performance of a closed-loop geothermal system. This information increases the accuracy of commercial ground loop designs in advance of thermal conductivity testing. Aeowyn also acts as a site safety officer as needed on test borehole sites and participates in geothermal inspections on larger installations. She holds a BS in physics from Messiah University and MS in Earth Sciences Hydrology from University of New Hampshire. Chris Winckler seeks to provide people with access to the next generation of heating and cooling systems while simultaneously making a great financial investment. Chris oversees all the residential sales and energy audit activities for Aztech Geothermal. And Chris studied business administration and management at the State University of New York at Oswego. And so with that, I'd like to hand it over to Chris to start with our presentation. Thank you for being here.
Awesome. Thank you for having us. I'd say for this presentation, even though I'm in charge of residential sales, for commercial stuff, I am also just boots on the street. So I'll get sent out to jobs like Framingham or projects that we have out in Colorado and walk around, look at houses for building conversion strategies, collect data to do heat load calculations, walk around, figure out where we're actually going to place the loops. So that way, as we're talking to cities or utilities, we can kind of give them an idea on where all this stuff is going to go and how it's going to fit together. And then Aeowyn, she's the brains of the operation along with John, and they'll do the actual hard crunching of the numbers and calculations to figure out exactly how deep and how many boreholes and where those boreholes are going to go to make these projects work properly. But yeah, we wear a lot of hats at Aztec, so it's for this presentation, that's kind of where we fit in. But anyway, thank you for coming to the Thermal Energy Network for local communities. There's Aeowyn and I on the screen. You're welcome to jot down our email addresses if you want to reach out with questions in the future. But you're also welcome to kind of cut us off and ask questions as we go. Our email addresses will also be at the end. So if you don't get them now, you can also get them later. Aztec, we've been around for about 20 years. I've been with them for about 15 or so. We have 4 AEE certified geo exchange designers, 5 IGSPA certified geo inspectors, and 9 IGSPA accredited installers, which for the longest time in the US was the most out of any company around. We're still kind of leading in that nature, but other companies are catching up to us. You can kind of see a list at the bottom of services that we offer. We do residential systems, but we've also, probably the past 8 years, have started to focus on mostly commercial design, and that's kind of direction our company's heading. Uh, Also do stuff like borehole testing and thermal conductivity testing, where we drill holes in the ground and figure out what that thermal conductivity is to help better design the whole ground loop system. So that's Aztech. Here's some of our partners that we've worked with in the past on the utility side. Our services have ranged from heavy in the design side to just being owners reps. I say just, where we help them make good decisions and we oversee what the engineers are recommending, and we'll help tweak that sometimes and direct it to whatever's better best for that pilot program. And then on some of these, all we do is we come in and we just do the thermal conductivity testing. So kind of a range of services for the utility side of things. Today's agenda. First, we'll talk about heat pumps 101, since I think that might be the most important part, is just to understand how heat pumps work. So then as you're thinking about your own buildings, you can start to see where they might fit in or where maybe they don't fit in. So you can see maybe there's certain buildings that make sense to convert, since they're easier to do so and easier, and ends up being a little bit less costly. Aeowyn will talk about thermal energy networks and how they work, also where they make sense. And then we'll also go and show some pictures and talk about the utility thermal energy network, which is really just the same thing as a thermal energy network, except owned by a utility. So it's really just a different financial model than a different installation model. So heat pumps. A heat pump is really just a refrigeration system that moves energy from one place to another. It does this by the expansion and contraction of refrigerant. So essentially, we're just using a little bit of electric to run refrigerant through a system. And if we're trying to heat, what we do is we end up taking energy from a cold place, we put it into a compressor, and then we compress the energy that we've gathered. And when you take a lot of energy from a big place and compress it into a small space, that energy or that refrigerant gets very hot. So we'll actually create about 120 to 140 degree refrigerant temperatures just by collecting energy and compressing it. We can then take that energy and that refrigerant and we can blow air over it. And that's the most common that we do. And that's a forced air system where we're heating or cooling through a ductwork system. But we can also put water over that refrigerant coil and create up to about 135, 140 degree water temperatures. There are some heat pumps that are coming out and more on the commercial side that can go hotter. But for today, with the energy or with the equipment that we know is robust, I'd say a good design temperature is between 135 and 140. On the opposite side of things, we can also gather energy from a place and we can put that energy into the refrigerant and we can put it through an expansion valve. And when you have something that's very hot and then you let it expand very quickly, that energy that used to be condensed is now in a very big space. So when it goes through that expansion valve and expands super quick, it actually gets very, very cold. And that's how we take hot energy through the refrigerant and create something cold that we can then blow air over to cool stuff. And some common ways that you can think about it, and these are just examples of heat pumps, is a refrigerator. If you've ever installed or looked at the back of your refrigerator, you'll see coils on the back of it. And really, those coils just have the hot refrigerant that are letting heat into your kitchen from inside of your refrigerator. And essentially, that refrigerant that's running through is expelling heat on the back of your refrigerator, which then cools down the refrigerant. That refrigerant goes into the expansion valve, and when it expands, it gets much colder. So when we blow the air from the refrigerator over it, we create cold, which also warms up the refrigerant to go back through that process. So that's just a way that we're taking and stealing energy from one spot and bringing it to another spot. Now, we'll talk a little bit later about COPs, which is really just what the efficiency is. And that really just determines how much electric are you putting in to what the benefit comes out. And since the heat pump is just moving from one to another, we can have 3, 4, 500% efficient systems. Unlike when you talk about a burning of fuel, you end up with, I mean, in best cases with natural gas, maybe at 95% efficient, but anyway, you're always below 100% efficiency. So that's why heat pumps are becoming more popular. As you also see here, air conditioners are also a form of heat pump. When you're talking about just a normal air conditioner, that doesn't have a reversing valve, so it's just an air conditioning unit. If you see one of these outside, that's a heat pump. The only difference is there's a reversing valve that allows the refrigerant to both heat the house and cool the house. It's really the only difference. Here's a very basic schematic of how things work. And if you think about air source heat pumps versus ground source heat pumps, they're actually the same technology. They're just getting their energy from a different place. And the reason that people go through the effort to dig a big pit or put boreholes in the ground to go geothermal, even though it's much more expensive, is if you look here. And essentially, if you're heating with an air source heat pump, that compressor has to work really hard to gather energy in -5-degree air, compress it to make that refrigerant hot enough to heat your house. Where if we're a geothermal system, we're already at 50 degrees. So that heat pump doesn't have to work nearly as hard to grab energy, compress it, and heat your house. Very basic, of course, but essentially we're just moving that 50 degrees and turning it into 120-degree refrigerant temperature. So when people ask, what temperature can you heat my house or my building? It's essentially any temperature you want, even though our design temperatures are usually between 70 and 72 degrees. Here's the opposite. Of course, we're collecting the heat from inside the house, even though we're putting cold air into the house. It's really doing so by us taking that heat and moving it through refrigerant into the ground. Also, if you're thinking about an air source system or a conventional system, to make 74 compress and expel that heat in a 95-degree air is just much more difficult and takes more energy to do so than it does to expel energy into 50 degrees. So that's kind of where we also get our efficiency bump, is we have about a 40 to 50% higher efficiency doing air conditioning with a ground source system than we do an air source system, only because it has to work less as hard. Same technology, it's just we're dumping that energy into 50-degree earth that just accepts it much easier. I'll skip over this because what I just talked about is just really a schematic with a conventional furnace and us tied into the ground. So drilling, there's many different types of drill rigs out there. This one happens to be just a conventional water well drill rig. And it's one form of ground loop that we do. And this house happens to be on Granite Street in Saratoga Springs, New York. And it's called Granite Street because 2 feet down from the grass is just granite. We hit bedrock almost instantly, which is both good and bad. We don't need a lot of casing, which is expensive, so that's good. But then we have to drill through bedrock, which can sometimes be a little bit slower than if we're drilling through an overburden like your typical loam and clay and whatnot. So yeah, here's one form of ground loop that we install. I'd say nowadays it's the most common. We used to be about 90% horizontal systems and only 10% vertical. We're now, because of mostly space reasons and just the cost is starting to come down on drilling, that we almost don't do these type of systems that you see on the screen. This is a horizontal system. We maybe do 1 or 2 of these a year. So 99% vertical with maybe 1%, if you want to call it that, less than 1% horizontal systems. And more for residential, even though we have seen them done in commercial aspects. But this is really, you dig down a certain depth below the frost line. At this house, it was somewhere between 5 or 6 feet, but we have other systems up north where we go 10 to 12 feet deep. And we just have to dig a certain size pit based on the energy that we're going to take out and heat that house with. So this ended up being a 3-ton system because you see 4 kind of separate loop systems here, which typically in the Northeast, we do 3+1 for a tonnage. And those are approximately 800 feet per loop. So we thought this slide was somewhat important just because it shows that there's nothing special about geothermal piping. Geothermal pipes are high density polyethylene. They're just slightly thicker wall than what's used for water pipes or gas pipes a lot of times. Uh, it's more just so a little bit more robust, I guess. But from an installation standpoint, utilities are very familiar with them. Most mechanical contractors very familiar with them. So we can usually take a company that's never installed geo and very quickly bring them up to speed on how to install geothermal systems because they've already done it. They're already certified. It's really just the design and what people are unfamiliar with is the depths that things have to go. How do you manifold lots of boreholes together? That's really the unknown for most people. The actual materials that are used and the way that they're put in the streets is all very common to water mains and gas pipes. So, for the most part, even though I like to think we're very specialized, 90% of what we do is very common. All right, at this point, I'm going to pass it off to my associate, Aeowyn. She's going to get a little bit more in depth with just what a thermal energy network is and how they're looked at. So I'll let her take that away.
Yeah, I did just want to jump in. We did have a question that came in about just the general advantages of horizontal over vertical.
Yep. Uh, Horizontal systems can be difficult mainly because A, you need a lot of space, and B, the substrate has to retain water very well. If you put a lot of pipes in something that's super sandy and is dry, there's just not enough contact of that sand. Like if you look on a microscopic level, there's lots of air around that sand. So even though we're moving water and it might be buried, there's not a ton of contact or energy to pull from. Whereas if it was an area that was a lot of clay tends to have very good interaction and hold water very well. So a clay horizontal system will perform equally and sometimes better than a vertical system, depending on what that vertical system is installed into. But as we start doing larger systems, you just don't have enough space to do a horizontal. And kind of to put it in a perspective, if you have an average, say, 2,000, 2,500-ish square foot house, the average pit that you would need to dig to heat that house ends up being somewhere between 40 and 50 feet wide by 100 feet long by 6 to 8 feet deep. So it tends to be, 3-4 times as big as what you would even need for a septic system if there wasn't city sewer available. So it's really just a lot of space required for a horizontal. Where for that same horizontal system I talked about, that 2,000 square foot house, a lot of times we can get away with a single 500-foot borehole, and that borehole is only 6 to 8 inches in diameter and takes up a very tiny footprint. So as we start looking at either bigger homes or in most cases cities, it's just much less of space required to get the thermal capacity that we need. So, and also going back, because of labor rates and gas prices, where horizontal systems used to save a lot of money to go that route, they actually are sometimes cost neutral or more expensive nowadays than drilling a vertical borehole because drillers just have become very efficient. So a lot of times they can come in and be out and have a single 500-foot borehole drilled in one day. You still need to loop and grout it, which takes another day or two, and trench it into the house. But the drilling itself is usually done in a single day in a single 500-foot borehole. So a much quicker installation as well.
Thanks, Chris. We did have two other questions I think we might be able to answer before we
Yep.
move on to the next section, if that's all right. So,
Yeah.
what is the minimum ambient temperature variation for a heat pump system to be technically feasible? And then also, besides water, which other liquids are suitable to use for a heat exchange?
Yeah. So, of course, my most favorite answer is it depends. But I'd say on residential systems, we usually target a minimum entering water temperature of around 32 degrees, so around freezing, which is why a lot of these systems have antifreeze in them. And that's because if you look at the temperature difference and the efficiency difference of installing for a higher temperature, say 40, the efficiency increase doesn't make sense from the financial increase of how much more borehole that you'll need. So designing to a higher water temperature on a residential system doesn't make sense. So we typically go to around 32 degrees, maybe 30 for a residential system. Uh, on commercial systems, they're actually much higher. Those are typically more in the 40-degree range is what we target. And that's mostly because you get some benefit from simultaneous heating and cooling. So as a residence is pulling energy and heating with it, so they're making the water colder. At the same time, you might have a high-rise building, and even in the middle of winter, as weird as it sounds, a lot of those high-rise buildings are actually air conditioning on the majority of the top floors. So they're actually putting hot water into the loop. So because of that simultaneous heating and cooling, there's a lot of benefit, and it's easier to keep a little bit warmer water temperatures without going into too much detail. There's also more heat in air conditioning because we also have to get rid of the heat created by the compressor into the water. Whereas when we're heating a house, that heat generated by the compressor is actually a benefit. So without getting into too much detail, it's easier to design a system that has simultaneous heating and cooling on a large scale than it is to do a small residence. So it just gives us an easier way to hit higher water temperatures.
And Chris, I think the other piece was they were wondering about what other liquids are suitable that you
Oh,
or
yep.
alternatives. Yeah.
So for the most part, it's just water. It's water with a little bit of propylene glycol is what we use, mostly because it's environmentally friendly. There's some glycerin-based antifreezes out there that people look at. There's alcohols like methylene alcohol that some people use. We've gotten away from that because if there's ever an issue, you don't really want some of these other antifreezes in your water supply. And also some of them, when you're moving them in large quantities, they're actually combustible. So it kind of creates a hazard just transporting a lot of these antifreezes, where even though propylene glycol might not be the very best from a viscosity standpoint, it's the best from it does very well in comparison at these water temperatures. And it's non-toxic. You can transport it without licenses. There's a whole bunch of other reasons why we like propylene glycol. But going back to the main part, it's mostly just water. It's usually 80 to 90% just water flowing through those pipes.
Thank you, Chris.
So I'm just going to explain now the thermal energy network concept. A thermal energy network is basically everything that Chris just talked about, but scaled up. So you've got several buildings that are all using one shared loop. It could be multiple or it could be just one. We'll get into that in just a minute. But it's typically going to be um, several different kinds of buildings, so probably not just all one type. And you've got your heat sources and sinks, so places that you can pull heat from or dump heat when you don't want it, which you can see some examples of right there. And you've got the actual loop or the piping that connects all of the buildings together. And you can also at times include electrical system upgrades with your thermal energy network infrastructure to make it even more efficient. Next slide, please, Chris. So this is just a slightly more detailed diagram that shows some different possibilities for things you can put on a thermal energy network. So if you go from top right all the way around, you can have your geothermal bore field, which would be a source and a sink, depending on what you need seasonally. And then you might have some housing units of different kinds. You come around after all that, your water temperature has changed. It's either higher or lower depending on the season. And yep, you can see his cursor right there. You've got the second bore field for another heat source or sink. Then you might have some public buildings like a community center, a steam plant, a pump station that pushes everything around. You could even have thermal storage or extra heat rejection. These are just possibilities. This is not based on a real system, but you could do something like this. Next slide, please. So just briefly, an overview of thermal energy networks. They're not a new technology at all. We've had district heating, which is what it used to be called, or thermal energy networks of a different kind for a very long time, over a century. So first generation district heating usually used steam, and in some places these are still being used and functioning. Second generation tended to use pressurized hot water. These are definitely also still in operation in plenty of places. Third generation, hot water, but not as hot and not pressurized. So it would be below the boiling point. Fourth generation is low temperature hot water. I know this doesn't sound low temperature. It is low temperature relative to the other stuff. And then we've got fourth generation district heating and cooling, where you add associated district cooling waste heat for heat source. And then finally, we've got some fifth generation district stuff. It's more complicated farther along. So this is really ambient temperature. So you can see there 50 to 86 Fahrenheit and can serve as a heating source or cooling sink for whatever's on your network. So the lower temperatures enable a higher coefficient of performance, which is what Chris was talking about earlier, where your heat pump will produce more output for the amount of electricity that it uses. And then the next point, please. And yep, just noting that we can provide heating and cooling with these fourth and fifth generation districts. So then we have two options for thermal energy networks, especially the more advanced versions. You can have a centralized system where the heat pump is, or the heat pumps are at a central plant and they produce hot or chilled liquid for the loop. And it's distributed to each of the buildings and structures along the loop for their needs. You can do heating only, which would be generally two-pipe system. You can do cooling only, or you can do heating and cooling, which would be supply and return pipes for heating and cooling. And then versus the centralized, you can have a decentralized or a distributed loop, which is kind of more what we saw on the previous diagram, where you can have low temperature ambient water distributed to each building. And the heat pumps in each building, instead of in the central location, provide the heating and the cooling and the hot water. And you can have this as a one pipe or a two pipe system. So those are just a couple different configurations for thermal energy networks. Just to go into a little more detail on the ambient network configuration, here's another diagram where you have an ambient loop, which would be just above freezing to just before it starts to get like hottish water or whatever your fluid circulation is, whether it's water or just water with a glycol. At that temperature, it would probably have an antifreeze in it. So you have your geothermal bore field in the top left, and you have another one potentially in the bottom right. And each one of those comes with a pump station to push the fluid around the loop. And then you've got different buildings along the loop. So it's just another visualization of the same thing. with a focus on the temperature differential that Chris was talking about earlier, where the whole system and the pumping rates are controlled by the delta T, or the temperature difference across the heat pumps. So for a utility, this is typically going to be a little lower. For a campus system like a university campus, it might be a little bit higher, but I will get to that in just a moment. Next slide, please. So before we get to utilities, we're going to talk briefly about where do thermal energy networks make sense. Network systems are typically best with ambient loops, that is, where you have three conditions that are present. You need to have commonly owned land and buildings, ideally. Diversity of loads, meaning different types of buildings that have different needs. So, like a supermarket is going to have a ton of refrigeration. A hospital will also have a lot of cooling need, whereas a bunch of housing, especially in this area of the country, is probably going to be mostly heating. So it does depend on the kind of housing and whether it's like an apartment building. Those tend to be more cooling than heating if they're new construction these days. But you also need the buildings to be relatively close to each other so that you're not sending miles of pipe and losing all of your heat when you're transferring it. Generally, thermal energy networks don't make as much sense if you don't have all three of these. If you're missing even one of them, it just becomes a little bit less practical. So occasionally you're going to have regulatory presence or considerations that might push for district heating or thermal energy networks, even if you don't have these conditions present. But from a technical feasibility standpoint, these are typically what we look at. All right, next slide. So here's an example of a classic diversity of loads situation where you've got four different buildings and you can see their loads here. So the red represents the heating need of that building over an entire year, and the blue represents the cooling need of that building over an entire year. As you can see, these four buildings have very different needs. Maybe the two on the right are a little more similar, but overall there's a lot of diversity here. And the top left has a lot of cooling need, whereas the bottom left has a lot of heating need. Let's go ahead and hit the next slide. And here you see the combined heating and cooling need of all four of those buildings, which actually turns out to be quite balanced, meaning that the heating and the cooling are similar over a year. And as it turns out, if you combine all of these buildings together, instead of doing them separately as like their own individual geothermal systems, you can achieve a 25% reduction in the total amount of boreholes or loops that you need. So that's just an example of why combining buildings with different heating and cooling needs can really be a good move for efficiency. So a little bit about legislation. In New York State, the Utility Thermal Energy Network and Jobs Act passed in 2022 and became law. So I'm just going to go over this briefly because the UTENJA is a big reason why a lot of thermal energy network projects are taking place at all. It is the same technology, but for utilities instead of just anybody at all. So it matters in New York State and in other states, as we will see. From 2022 to 2023, the 7 largest utilities in New York State had to propose pilot projects. Around April 24, 9 of those projects advanced from the just proposal feasibility stage to the engineering phase. 2025, utilities had to submit detailed engineering plans for, at that point, 9 projects across the state. Then for the 2026 budget year, 200 million has been allocated to thermal energy network projects across state campuses, which is a big deal. That's really great. And today we have a bunch of projects that are awaiting final approval for construction and final design construction to begin. Next slide, please. So 13 other states, or 13 states total, 12 other states, have now either filed or passed legislation, or a couple of them are just considering it, for utility thermal energy networks, or in some cases, just thermal energy networks, but mostly it's utilities. So this map comes from the Building Decarbonization Coalition and in conjunction with HEAT, which is another organization doing great research in this space. And you can just go to their website and check out all these different states that are working on advancing thermal energy network legislation. Next slide, please. So neighborhood scale decarbonization is kind of a term to use instead of thermal energy networks in places where it's not quite a thermal energy network, but it's similar to one or there's some overlap. Basically, these are thermal energy networks, adjacent projects, and you can just see that on the map. They're really happening all over the place. There are a few states that don't have any right now, but they are growing all the time, and there's a ton of them in the Northeast. New York is a big leader for thermal energy networks and utility thermal energy networks. Next slide, please. Yeah, so I kind of just talked about that. We'll just go ahead and go to the next one. I just have some examples here of utility thermal energy network projects that have been done or are in the process of being done in New York State. So NYSEG, which is out near Ithaca, has their proposed project out there. This just shows a diagram of like a downtown-ish area in Ithaca where a bunch of buildings are planned to be connected to each other. And it's an open loop system, so it's actually a little bit different, which is kind of cool, with 8 supply and 8 discharge wells, because there is a massive aquifer under Ithaca that is a fantastic thermal resource and can be used for this U10 project. So this project would include 39 buildings, 8 of which are not residential, and 31 basically just houses. So next slide. There's a pilot project proposal for Troy, New York as well. 5 proposed buildings, single pipe ambient temp, which hopefully we recall from earlier in the presentation, is like a 5th generation thermal energy network. This would have a large number of boreholes at around 600 feet deep and have a large main pipe, which is what the 16-inch is referring to here. So that would be in Troy, New York, by the river. Next slide, please. So down in Poughkeepsie, Central Hudson, which is another utility, has another proposed pilot project, which we worked on with Labella, an engineering associate firm. They are currently looking at doing 12 commercial buildings, 7 residential buildings, which would be apartment buildings, with dry fluid coolers to keep the loads a little bit better balanced, but it's mainly just closed loop geothermal boreholes. And you can see those tiny little circles on the figure represent the boreholes, and there are like a bunch of different bore fields on this figure because they're all spread out to be a little more distributed along the loop and just generally where they could fit. All right, next slide.
Framingham, this is a system that we install, or has been installed. I shouldn't say we installed it. So phase 1 is actually completed, which the rate case started in 2021 and site selection in 21. But I'm going to run on the notion of time. I'm going to run through this relatively quickly so that way I can show you pictures of what an install looks like and then just kind of relate it better to what that looks like for you if you're looking at converting some of your commercial properties. So anyway, up top here, we have a lot of angled boreholes, which I'll show you pictures of how those were installed. That ends up letting us not use up a lot of space on the surface, but allows us to get energy from a huge area. And as long as you own the whole area, we can then get access to energy underneath different buildings without actually ripping up those buildings, which is great. Uh, and then it makes manifolding easier, makes connecting the pipes to the loop easier. So it actually makes some stuff a little bit less expensive. And the drilling aspect isn't very much more expensive. So a lot more benefit to doing this. The only downfall is not many drillers can do it. So if you do angled, you don't have a big of a selection to get quotes from. Rolling through. So here was the original geothermal pilot. We had a bunch of residential buildings. We had the fire department. We had a gas station, which helped offload some simultaneous heating and cooling, corner cabinet, and a public school. But this was the main one. And I was in every single one of these houses. We did the manual J heat loads. We looked at the building conversions. That's kind of the hardest part is, putting pipes in the ground, something that's utilities are used to doing. It, of course, has its own complication, but they can figure that out. The hardest part when you're thinking about a conversion is how easy or how difficult is converting the buildings themselves to geothermal, because that's where the huge difference in cost could happen. Luckily, since a lot of these were residential units and we could convert them to ductwork systems relatively inexpensively, and then a lot of the housing authority and the fire department was easy to accept the lower temperatures of geo, that it made this area relatively straightforward to convert. Good enough to the part where we're now actually in the middle of the expansion process. And this is moving forward. So they have funding for it. I forget exactly where they are. We are being brought back into the process. So we'll be brought out on site to help kick this off eventually. But right now, this is moving forward. And it's kind of exciting because it was the first 1A to be installed, besides for a couple smaller, I guess you could argue, district systems. But this one's actually going to phase 2, which, shows progress, which is what we want. All right. So when you're thinking about installing a system on your own property, and you're like, what are the main things that we want to look at? Do you have space? Especially for large buildings that have large energy costs, you're going to need a large amount of space or large amount of access to space. So even though we have the ability to drill on an angle, if you don't own the space that you're drilling under, you're technically not allowed to access the energy underneath it, because what if your neighbor wants to do a geothermal system? They own the energy below them. So the one kind of nice thing about working with either a utility scale is once you get people to sign on, you can get kind of right of way access agreements to say, we're going to connect you up, but you need to give us access to space beneath your property. And that's how we kind of get away with that huge network of angled boreholes that goes out underneath all these properties. Kind of related to something, if you look at a college campus, they have tons of different buildings that are doing different things, and they have lots of space. So it's kind of easy for them because there's one owner, which makes things much more straightforward. There's a lot of space, so there's room for boreholes. And the other most important one, which actually, I'll skip that one. The other most important one is diversity of load. So if you're going to do a huge network of systems and they're all heating dominated, so they're not actually helping each other, they're all just making that loop colder, and there's no real benefit to connecting them. You'd actually get more benefit out of popping in some boreholes that are just serving each of these buildings individually, because the cost to connect them and do pumping stations and manifolding ends up just increasing the cost to convert those dramatically. But if you have diversity of load, like you have a grocery store, you have, I don't want to say it out loud because people hate them, but you have a data center, or you have, college campus, you have a computer center or something that has a lot of energy loss and a lot of air conditioning required even in the wintertime, that's when it starts to make sense to combine them, because that's when it's going to reduce the amount of drilling required. So even though you'll have more cost to connect them and to manifold everything together, you save a lot on the drilling costs, and that's what makes it more feasible. So if you only have heating dominated buildings, it probably makes more sense just to do individual conversions. As much as I don't like to say that out loud, because everyone thinks that 10 projects are just the hot new thing. Here's kind of a cool picture. So this is them drilling at an angle. And for the most part, we're somewhere between 7 and 12 degrees for the most part, because even if you're just 7 degrees off while you're drilling, when you're going 500, 800, 1,000 feet down, that ends up being, hundreds of feet apart from each other. So even though we could be 10 feet from each other on the surface, they'll be hundreds of feet apart, accessing a lot more energy below, which gives us access to more energy than if you had a lot of vertical boreholes in a grid pattern. Because if you think about it, those boreholes on the inside are don't have access to a lot of thermal energy around them, because they're insulated by the ones outside of them. So if everything goes down vertically, you need a lot more boreholes than if you started to spread them out and they have access and can recover quicker due to just more energy available. So going with angle drilling has helped a lot from the number of boreholes required and the space required that you need. So that stuff's pretty cool. And then installation. You need to be able to dig and cut up streets and get this pipe installed somewhere, which goes around the entire perimeter. So when you're thinking about what areas or what buildings you want to convert, keep in mind that you have to dig a trench that goes around the entire perimeter, or at least pretty close by to whatever buildings you want to connect to the system. So this one is actual pictures from Framingham. It's a single pipe. So that's our single 8-inch pipe going through the street. We had to make sure that we're not interfering with other utilities. And where we did, as you can see, they had to repair this natural gas line, which is something they're used to when installing new utilities. But something to consider is a lot of times in the city street, there is so many other utilities that you have to figure out where to put stuff, which is why once you move to just a private entity like a college or whatnot, there's just a lot less stuff buried that's in the way that you have to think about. Here's somebody butt fusing. It's called fusion welding, but essentially all that they're doing is melting two pipes together. And that melted connection, since it pushes together and kind of mushrooms on each side a little bit, that connection actually ends up being stronger than the pipe itself. So doing it this way actually creates a very, very strong bond between the pipe. And then once it's all installed, you'll have some of these caps. Those caps are essentially just a curb stop valve. So as you have a connection, a supply and a return to a customer's house, if that customer ever has to get service, and this customer could be a residential building or a commercial building, if they ever need a service something or swap out a heat pump, they can shut off the water at the main. That way, if they get air in the system, you're not getting air in the main distribution pipe, which can cause some issues down the road. It makes things easier to purge and essentially just take care of in the future. And that's it for us. I hope we gave you enough information that now you have lots of questions. And I know we don't have a ton of time, but feel free to ask us whatever you want. And of course, like we said before, there's our email addresses. So even if you just have a couple buildings or some ideas that you want to run by us and say, hey, does this make sense looking into, connecting them into a thermal energy network, or should we do them individually? We can, just from Google Earth and a little bit of information from you, we can determine, which way kind of makes sense to start investigating first, and we might say it depends and want to look at both, but usually we'll have an opinion on what makes sense to look at first. So.
So Chris, we do have a couple of questions in the Q&A and we have one in the chat. Josh, do you want us to go in a particular order?
Yeah, we could just start with looks like the one that came in first. Looks like once an individual heat pump system has already been installed, what does it take to convert that into a shared system for a 10? And is there any situation in which that makes sense to do technically or financially?
So we actually just did an installation in Sheridan Hollow in Albany, where we connected a housing authority building, which is just a single residence, to a commercial building, which was really a 3-floor complex that was a hair salon and then 2 apartments above it. And we did that in a way where they're actually both on a single ground loop, which could also just be, this could be just a house too on a single ground loop. But the idea is we did it in a way that the idea is to convert most of Sheridan Hollow to a district system or a thermal energy network system, that we can connect that and use their ground loop as another recharge point. So when Aeowyn mentioned before how you have different scattered reinjection points or recharge points throughout the system, anywhere that has a geothermal system and anywhere that has a vertical borehole with a pumping station in the basement, like most do, essentially we can then, instead of having it go directly to their heat pumps, we can have it go to a heat exchanger, which then goes outside to the main. So without getting into too much detail, any system and any existing geothermal system, as long as we have access to the infrastructure, like say in a basement, we can make that part of a thermal energy network.
Thank you for that. I think we have time for one more, and the reliability and lifespan of a geothermal heating system versus their traditional HVAC.
Geothermal heat pumps are rated for 25 years, their lifespan, just like conventional equipment is rated for 15 years. The reason that our system is rated, or I say ours, the reason geothermal systems are rated for a longer lifespan is because if you compare it to a furnace or a boiler, we don't get as hot. So there's not as much expansion and contraction on the heat exchangers inside of our equipment. And then if you look at it compared to air source equipment, all geothermal systems are protected and all the equipment's in a nice basement or a mechanical room on the first floor. It's not out in the elements. And air source heat pumps, they're collecting energy from the air outside. So they're getting snowed on and rained on. And as the rain falls, dirt's getting kicked up into the heat exchangers, and everything just, has a lot more stuff to fight than a geothermal system. And the only thing that we have that's in the ground that could hurt our longevity is plastic pipe. So the plastic pipe itself and the ground loop itself, just like natural gas infrastructure that they're installing, they write that infrastructure off over a 50-year period. So that ground loop stuff can be expected to last at least 50 years, even though it should last hundreds of years. So that infrastructure essentially past our generations. Whereas the inside equipment, we're usually about 10 to 15 years longer of a lifespan.
All right. Well, thank you, Chris and Aeowyn, for a great presentation, plugging our next part of the webinar series in September for the first Wednesday of the month, same time. We'll be looking at local climate action planning for your municipality. And like I mentioned earlier, the recording for this will be sent out soon. And I want to thank again our speakers for their time and expertise, and our attendees for attending the session of the Climate Action Webinar Series. And we hope to see you at the next one. Thank you.